Welcome to the 8th lecture of our Natural Disasters course. It's in this lecture that we switch gears. We have focused on those disasters that are driven by interior energy, energy from within Earth's interior, that is energy from its leftover from its formation, and the heat produced by radioactive decay inside Earth's interior. From here on out, we'll be focusing on disasters that are driven by external energy, which is radiation from the sun. And so in this lecture, we introduce and familiarize ourselves with the solar radiation, how it interacts with the atmosphere. And using that understanding, we will be able to apply it to other disasters such as storms, which there's different variations of storms. You know, you have thunderstorms, cyclones, and hurricanes, and so forth. And we'll have some understanding of applications to climate as well. So we'll be talking about external energy and how it fuels weather and climate. So first, we're going to make the distinction between weather and climate. So weather includes short-term processes. So these are processes that occur over the course of, anywhere from several minutes, several hours, or maybe even several days, right? So we have tornadoes, heat waves, hurricanes, floods. Those are all examples of short-term processes known as weather. The weather changes fairly rapidly, day to day, hour to hour. On the other hand, climate refers to long-term processes. So periods of generally cooler temperatures on Earth, known as ice ages, generally warmer periods on Earth, known as torrid ages, droughts, which is reduction in the amount of precipitation, changes in the atmosphere, and also shifts in ocean circulation have impacts on climate as well. So in this chart, we see energy flow to and from the Earth. So in the left-hand column, we see solar radiation, heat flow from the interior, and then tidal energy. Tidal energy is the energy from the pull of the moon and the sun on Earth, the gravitational pull of the moon and sun on Earth. Where solar radiation is basically, well, part of it is the light we see coming from the sun, but as we'll see, it's more than just the visible light. But solar radiation is the energy coming from the sun. Heat flow from the interior, that's the interior energy that drives plate tectonics, right? That's heat that was trapped in Earth's interior from its formation and produced in its interior from radioactive decay. So we see there's direct reflection. So that's radiation that's reflected from off of either parts of the atmosphere or the Earth's surface. There's energy that is converted into heat, or solar radiation that is converted into heat. There is solar radiation that is absorbed to evaporate water. There is solar radiation that is absorbed that results in the motion of water in the ocean and atmosphere. Then there is the solar radiation that's absorbed by vegetation and algae in the process of photosynthesis. And so the total energy flow in times 10 to the 12th joules per second is in this middle column. Now, what is a joule? A joule is a unit of energy, okay? So energy takes many different forms. There is the energy due to a certain position, say potential energy, right? If you lift something higher off the ground, it's higher potential energy. There's the energy associated with motion, that's called kinetic energy. There is also electric potential energy, right? Or magnetic potential energy. So electric-magnetic fields exert forces on objects and they create potential fields, which gives potential energy. Then there is Chemical potential energy, that's the energy that's stored in chemical molecules. And then, so example of chemical potential energy is the food stored in our, the energy stored in our food, right? If you look at a granola bar in the nutrition facts, you have the number of calories in that granola bar. Say there's 100 calories. Well, calorie, that's a with a capital C, that's a food calorie. That's 1,000 calories with the lower C, which is the scientific unit of energy. So a calorie is a unit of energy, right? You can convert it to joules. I believe there's I forget the conversion, but maybe like 4 and change, 4.184 or something, or joules per every calorie. I'm not sure in that conversion, but calorie is just one unit of energy, where joule is another unit of energy, right? So energy can take many different forms. The form of energy coming from the Earth is in the form of electromagnetic radiation, which is electromagnetic fields or waves that are coming from the sun to the Earth. You can see, so this is energy flow in times 10 to the 12 joules per second. Right, so there is a significantly more solar radiation than heat flow from the interior and tidal energy. Solar radiation accounts for over 99% of the energy flow to or from Earth's surface. So solar radiation is in no means trivial, right? Neither is an internal heat flow. Remember, this is just heat either coming to or leaving the surface. The internal heat is significant enough, and that heat is energy, which heat is a form of energy, is significant enough to drive plate tectonics and result in earthquakes and volcanoes and all those disasters. But the amount of solar radiation is extremely, extremely large. So solar radiation received by Earth. So electromagnetic waves are, just as they sound, they're waves. But like other waves, like we said with seismic waves, they have a frequency as well. All right. And you also have a wavelength. Okay. And so frequency is proportional to wavelength. So for a wave, a wave travels with a speed, say v. Oh, I wish I could get my pen to work. Travels with the speed v. And the speed is equal to the wavelength, which is represented by the Greek letter lambda, times the frequency. Now for light, the speed is constant. It's the speed of light. Light always travels at the same speed through a given medium, right? And that's the speed of light. So this number is always the same. So with that said, if a light wave or electromagnetic wave, so electromagnetic wave and light, those two terms are synonymous. Light is an electromagnetic wave. An electromagnetic wave is light, all right, what we call light. And so the frequency of that light wave or electromagnetic wave is inversely proportional to the wavelength, because the product of the two equals the speed. What that means is we have a large large frequency, it has to have a small wavelength to equal the same speed. If we have a large wavelength, we have to have a small frequency to have the same speed. So waves that have large frequencies have very small wavelengths, and waves that have small frequencies have large wavelengths. Now, with light waves, the energy associated with that wave is proportional to the frequency. The energy is actually equal to Planck's constant times the frequency. If you're familiar with Planck's constant from physics, but it's directly proportional to the frequency. So the higher the frequency, the more energetic electromagnetic wave with a light. And so where does that in terms of wavelength? Well, if we're going to have a high frequency, large frequency, that corresponds to small wavelengths. So small wavelengths are high energy, and long wavelengths are low energy. So here we have wavelength plotted in micrometers. So here's 10 to the 0. So that's 1 micrometer right there. Anything to the 0 is 1. This is 10 to the negative 2, right? So that's 1 all over 100. So that's 1/100th of a micrometer. This is 10 to the negative 4. This is 10 to the negative 6, right? That's 1, 2, 6 micrometers, right? That's very small. So this is very small wavelength, and so this is large frequency. That's supposed to be a lambda. But over here, we have large wavelengths, right? This is 100 micrometers. This is 1, 2, 3, 4. That's 10,000 micrometers. And this is 1,000,000 micrometers, right? So these are large wavelengths, small frequencies. So this is on energy. This is higher energy. This is lower energy. All right. And so different frequencies, or I should say, this range of frequency in which electromagnetic radiation or light exists is called a spectrum, the spectrum of electromagnetic radiation. In other words, the spectrum of light. Different frequency ranges are given different names. For example, this little tiny range in frequency here, if you expand it and look at it, this is the frequency, range and frequency of electromagnetic radiation that our eyes are sensitive to. And we call this the visible spectrum, because this is the spectrum of light that we can see. Now, light with lower frequencies is called infrared. That is, if you ever heard of infrared goggles, those are goggles that are sensitive to infrared light. And there's certain animals that are sensitive to, their eyes are sensitive to infrared light. Like, for example, snakes. Snakes can see infrared light. You can basically think of infrared light as heat. So warm objects radiate infrared. And so we readily absorb infrared heat, and so we can actually feel that infrared radiation. If you go even lower, you have microwaves, and you also have radio waves. So radio waves are really long wavelength light. Then above the visible spectrum, we have ultraviolet, and we have X-rays, and then gamma rays. So X-rays and gamma rays are really high energy light. And within the visible spectrum, red is the lowest energy light, and violet is the highest energy light. That's why ultraviolet light, well, I should say, the spectrum of light from the sun that makes it to Earth's surface ranges mostly from infrared to ultraviolet. So when you're standing outside on a sunny day, you know, all the light that's bouncing off objects around you that look red, object that looks red, that means that object is absorbing all frequencies of light except red. It's like only red is bouncing back to you. If an object is blue, it's absorbing all frequencies of light except blue. That's why white objects warm up the coolest, because it reflects all light back. So when you put all these colors together, Roy G. Biv, you put them together, it's white light. And if an object looks white, that means it's reflecting all the visible frequencies of light back. If an object is black in color, that means it's absorbing all the frequencies. That's why black objects heat up much faster in the sun than white objects, because they absorb more of the light. And what happens whenever light is absorbed? Well, the light is energy. The energy is converted from electromagnetic radiation or energy to heat. And so whenever we're standing out in the sun and we see all the visible light, the heat we're feeling from the sun, that warmth that you feel, that's the infrared radiation. Then the ultraviolet you can't see, but you have to protect yourself from it, right? You put on sunscreen, you wear a hat, because the ultraviolet radiation is high enough energy that whenever it's absorbed by the cells of your skin, it kills your skin cells. And so it does damage to your skin. And if you just get a little bit, it kills the outer layer of skin. And as they begin to decompose, they turn brown, giving you a suntan. If you get too much ultraviolet light, it kills not only the superficial skin cells beneath the just beneath the surface, but it starts to kill tissue cells deeper, and it gives you a sunburn, right? So you have to protect yourself from the ultraviolet light. So that's the solar radiation received by Earth. We do receive some radio waves. So sometimes if you have static on the radio, you get some solar radiation in the form of radio waves. And the higher energy stuff, X-rays and gamma rays, a lot of that is filtered out by the Earth's geomagnetic field. So the sun radiates energy and electromagnetic radiation. It's generated by, I should say, hydrogen fusion. So hydrogen atoms are fused into helium atoms, and as a result, in the sun, it releases energy. Form of electromagnetic radiation. It comes to the sun, comes to the sun, it comes to the Earth. So this is the energy received by Earth from the sun. So 100% of that energy, of it, 30% is reflected or scattered back to space. Okay, where 70% is absorbed at some level in the Earth system. 16% is absorbed by the air itself, air molecules. 4% is absorbed by clouds. 50% is absorbed by the surface. Right, so there is our 70% that's absorbed. And remember, what happens whenever light is absorbed? Well, it's converted into heat. And so this is how the Earth is heated. Now, where is the largest amount of energy being absorbed? By the surface. And so most people think that the atmosphere is warm because the sun warms the atmosphere. What really happens is the sun's energy is absorbed by the surface of Earth, and it warms Earth's surface. And then as a result, the Earth's surface radiates off infrared light, which that infrared light is much easier absorbed by the atmosphere, and that warms the atmosphere. So the light is absorbed by the Earth's surface, increasing the temperature of the Earth's surface. As a result, the Earth's surface begins to radiate off infrared light, and that infrared light is absorbed by the atmosphere and warms the atmosphere. And so it's this heating of the sun that powers the hydrologic cycle, along with gravity, and so the movement of water and the atmosphere. However, what's really important is that the sun heats the Earth's surface unequally. It's not that the solar radiation is stronger or weaker at different parts of the Earth. What's different is the fact that the Earth's surface is curved, and the light from the sun is coming into the surface at a different angle in different parts of the Earth. So let's use this flashlight as an example. So this flashlight is radiating light. And so this light is a certain amount of energy. And if this flashlight is pointed directly towards the surface, the light radiates down, and that light is being absorbed by the area of the surface the light is in contact with, or it's impinging upon. And so let's call this area 1 unit of area. So we have this amount of energy. Let's call it E. Get my pen back up. This amount of energy, let's call it E, being absorbed by 1 unit of energy. So the energy per unit area being absorbed is E over 1, or just E. That's the energy per unit area being absorbed. Let's take the same flashlight, which is radiating the same amount of energy, but now it's hitting the surface at a 45-degree angle. As you can see, as a result, the area which that light is spread across, that it's impinging on the surface, is now larger. It's 1.4 units of area. So the energy per unit area is 1 over E over 1.4. So this is the energy per unit area, and you can see it's less, right? This was E, this is E divided by 1.4. Let's say if E is 1, we just normalize it, then 1 divided by 1.4, so this would equal 1, this would equal 0.714. So you can see it's about 3/4, a little less than 3/4 of the amount of energy per unit area being absorbed. right? Where in this case, if we change the angle which the light is hitting the surface, now it's the same amount of energy, now it's being spread out over 2 units of area at a 30-degree angle. Now the energy per unit area is E over 2, which is equal to, if we say E is equal to 1, 0.5. So it's half the amount of energy per unit area. So remember that whenever the energy is absorbed, the light is absorbed by the surface, it's converted into heat. It's heating the surface. So which surface is going to get warmer? This surface is going to get warmer, right? If you put your hand right here, it will feel warmer than if you put your hand right here, right? Because this is double the amount of energy per area being absorbed here than here. Why? Same amount of energy, but it's being spread over twice the amount of area. So the angle that the sunlight hits the Earth's surface determines how much the light is spread over the surface of the Earth, and therefore how much energy per unit area is absorbed. So the Earth is sufficiently far enough away from the sun that all of the light rays or waves coming to Earth from the sun are parallel to each other, traveling in a straight line. And you can see where on Earth they hit the surface, the light is impinging on the Earth at a different angle. This is 90 degrees, and so this is E. This is the full amount of E. Or if this is 45 degree angle, and if say E is 1, this is 100. Let's say just as 1. This is a 45 degree. We saw in the last one that it's about 0.714 units of energy per unit area. So about 3/4. And here, right, look, the light is actually parallel to the surface. So if the light's parallel to the surface, how much of the light is hitting the surface? None. So it's 0. So the amount of energy per unit area is a maximum where the sun's rays are hitting the Earth's surface at a 90-degree angle, and the amount of energy per unit area decreases as a function of latitude. Remember, latitude are the lines that are parallel to each other, that the equator is 0 degrees latitude, the North Pole is 90 degrees north latitude, the South Pole is 90 degrees south latitude. So the amount of energy per unit area decreases as a function of latitude. It gets maximum at 0 degrees, or it's not always 0 degrees at latitude, as we'll see, because the Earth's tilted on its axis and so forth. But it's wherever the light is intersecting the surface at a 90-degree angle, that's where it's maximum, and it decreases as you go away from it. So that's why it's warmest here and it's coolest here, right? There's no less light here than there is here. The difference is the angle, how spread that light is over the surface. How much energy per unit area is being absorbed. So here we can look at the amounts of radiation, or amounts of energy absorbed by the Earth's surface, and then the amounts of radiation lost by Earth's surface as a function of latitude. So here is 0 degrees latitude, that's the equator, right? And so there's 9 degrees north, that's North Pole, 9 degrees south, that's the South Pole. Here you see between about 38 degrees north and 38 degrees south, the amount of energy absorbed is greater than the amount of energy released. So as a result, there is a net heat surplus. And so there's a net heat surplus. So there's excess heat within this region. However, if you go at higher latitudes, at 39 degrees north or higher, 39 degrees south or higher, the amount of energy absorbed is less than the amount of energy lost. So there's a net heat deficit. There's a net heat deficit here. And so a law of thermodynamics is that heat flows from hot to cold. So heat is going to flow from low latitudes to high latitudes on Earth. And that heat flows Well, that heat doesn't move itself. Warm material moves, transports that heat. So it's warm air moves from here to here. Warm water moves from here to here to here. So that's how atmospheric circulation is generated. That's how oceanic circulation is generated. The air is warmer in the tropics near the equator, and the air is cooler at the higher latitudes, and so the air circulates in order to move that heat from where there's a heat excess to where there's a heat deficit. The same thing happens in the ocean. All right, and so solar radiation received by Earth is also influenced by climatic feedbacks. Okay, so now sometimes people say, oh, the ice caps are melting. It's like, yeah, is it that big of a deal? I don't know. But people don't realize is that it's a non-linear process, the melting or formation of polar ice caps. What does non-linear mean? It means it doesn't happen at a consistent pace. Non-linear means something can happen slower as time goes on, or as a function of whatever variable, or it can either happen slower or it can happen faster. Unfortunately, the melting of the ice caps it rises exponentially. It's not linear. And why this is because remember how I said white objects are white because they reflect all frequencies of light and they don't absorb much light? That's why they're cooler, right? You get into a white car in the summer, it's not as hot as getting into a black car in the summer. Well, snow and ice is white. And the amount of light that's reflected by a surface is called its albedo. So white surfaces have a high albedo, where dark surfaces, like brown, dark blue, which happens to be the color of the ocean, or greens, they have lower albedos. They absorb more light and reflect less light. Well, regions, if the Earth begins to receive less solar radiation, then it'll become a little bit cooler. Because it's a little bit cooler, it'll develop more ice and snow. That little bit larger amount of ice and snow will cause a higher albedo or reflectivity and result in less energy being absorbed by Earth's surface, more energy being reflected, and as a result, cause it to cool a little bit more, causing even more ice and snow to form, which causes more solar radiation to be reflected, which causes it to cool even more, which causes the formation of even more ice and snow, reflects more energy, causes it to get even cooler, more ice and snow reflects more energy, causes it to get even cooler. And you can see it's a positive feedback loop. It begins to, no pun intended, snowball. The opposite process occurs too. If the Earth's climate begins to warm, maybe there's a little bit extra solar radiation, or there's some other extra heat. You know, we have the warming of the atmosphere through the greenhouse effect. If there's a little bit extra heat, that melts a little bit more ice and snow, which causes a little bit more solar radiation to be absorbed, which causes the Earth's atmosphere to be a little bit warmer, which causes a little bit more ice and snow to melt, which causes it to absorb even more energy. So it's a little bit warmer, causes a little bit more ice and snow to melt, which causes it to absorb more energy, and so it feeds off itself in the opposite direction. So it's this climactic feedback loop. So there is a point called the point of no return where once a certain amount of the polar ice melts, even if warming stopped, that's it. This feedback loop will cause the rest of the ice to melt, even if the Earth's climate did not continue to warm at all, right? It just feedback loop will run its cycle and all of the polar ice caps will be melted. So where that point of no return is, no one is exactly sure, but once it's crossed, it is frost, right? And so throughout Earth's history, the amount of solar radiation it has received has changed, as we'll look at when we look at climate change, through natural phenomena. And that has caused these cycles, these feedback loops to occur, causing warming of the Earth and then cooling of the Earth, throwing it into and out of ice ages through natural phenomena, as we'll see. So the greenhouse effect is very important and necessary on Earth. You might hear the greenhouse effect in a negative connotation. That's because, well, too much of a good thing is a bad thing, but we need some greenhouse effect, right? Solar radiation reaches the Earth as short wavelengths, okay? So it's most of it's visible in ultraviolet light. It's absorbed by Earth's surface, increasing the temperature of Earth's surface. Then Earth's surface re-radiates that energy in the form of a long wavelength infrared light. Well, infrared light is very readily absorbed by particular molecules like water molecules, carbon dioxide molecules, and methane molecules in the atmosphere. Whenever they absorb that infrared light, they get excited, they warm up, and they re-radiate that heat back down to Earth's surface. And so that is the greenhouse effect. It's whenever certain gases called greenhouse gases act almost like glass. Glass allows visible light, ultraviolet light, to pass through, but infrared light has a harder time passing through the glass. So if this is a glass surface, really short wavelength light can pass through it. It's a surface absorbs it, it warms, and then that surface radiates long wavelength light that is then reflected back down by the glass. And so this long wavelength light is basically, that's heat, right? It's heat. So it accumulates and it warms inside the greenhouse. So greenhouse gases serve the same role as that pane of glass. Whenever the infrared light is radiated from the Earth, it's absorbed by the greenhouse gases and re-radiated back down. So they kind of act as a blanket, right? That's how a blanket works. A blanket doesn't produce any heat. What it does is it traps the heat that you are radiating and holds it close to your body, so it feels warm. Greenhouse gases do the same thing. They trap the heat that the Earth is radiating and hold it close to the Earth, preventing it from escaping to space. So the more greenhouse gases you have in the atmosphere, it's like having a thicker blanket on. More and more heat is trapped, and therefore the temperature increases. We need the greenhouse effect. If it wasn't for the greenhouse effect, it would be very cold. It wouldn't be warm enough for liquid or water or water vapor, and it would not be inhabitable. We need the greenhouse effect. And so without the greenhouse effect, it wouldn't be here, but like I said, too much of a good thing can be a bad thing. So solar radiation is received by Earth. So 99% of the energy Earth radiates off, 6% just goes to space. 99% is absorbed by clouds, and once it's absorbed by clouds, 38% is by the air in clouds. 38% of the energy is radiated from the air to space. 26% of the energy is radiated from clouds to space. But 85% is radiated back down. Okay, so that's the heat that's captured and radiated back down, and that's the greenhouse effect. So now we understand the role of solar energy, radiation, and how it heats the Earth, and how the atmosphere is warm, how it stays warm. Now we're going to look at how water and heat interact on Earth, because this interaction is extremely important. So there is a certain amount of heat that's required to raise the temperature of any substance. Okay, if you have 1 gram of a substance, the amount of heat that's required to increase its temperature is called its specific heat. All right, and so the required amount of heat to raise the temperature of 1 gram of a substance is called, oh, I should say, the amount of heat required to increase the temperature of 1 gram of a substance by 1 degree centigrade is the specific heat. And so water has a relatively high specific heat compared to other objects, other materials. As you can see here, here's the specific heat. Water is 1, right? That's much higher than granite, which you can think of as stone. Quartz is basically stone, and air is 0.24. Water is about 5 times higher specific heat than stone. And there's different ways in which heat can be transported. There's convection. This is the transmission of heat through the flowing of air or water. So heat can be moved from location A. Let me get my pen back up here. Location A oh, I'm sorry, my pen isn't working. So location A to location B by warm air moving from A to B. So it's the movement of air, warm air or water from A to B that's transmitting the heat. That's convection. Conduction is heat traveling through contact. So if you have heat, if you have like a warm surface and you place a piece of metal on that surface, heat transmits from that surface into the metal, warming the metal. That's the conduction of heat. Right? And so, and then you could see how the different heat capacities or specific heats vary among materials, like for example, sand and water. Ever go to the beach on a hot day and you walk on the sand and it's so hot, it's burning your feet? That's the dry sand. But once you get in the wet sand, it's nice. It's so much cooler, right? The difference is the wet sand's mixed with water, and the water has a higher specific heat, so it has to absorb 5 times. Sorry, it has a specific heat roughly 5 times larger than that of sand. So water has to absorb 5 times as much energy to increase in temperature than sand does. Conversely, you can think about it this way. Sand increases in temperature 5 times faster than water when absorbing the same amount of energy. So both 1 gram of sand, 1 gram of water, they absorb a certain amount of energy. The temperature of sand will increase 5 times more than the temperature of water because it's lower heat. That's why the dry sand gets so hot, because its temperature increases so much more rapidly than the water does. The water vapor in the atmosphere ranges between 0 and 4% by volume. And we quantify the amount of water vapor in the atmosphere with what we call humidity. Now, there's different types of humidity. There is the absolute humidity, which is the absolute amount of water vapor in the air. That is rarely ever used. The relative humidity is, I should say, but before I get to relative humidity, the saturation humidity is the maximum amount of water vapor that the air can hold. All right, so this isn't the amount of water vapor in the air. This is the maximum amount of water vapor the air can hold. This is a function of temperature. So the higher the temperature of the air, the warmer the air, the more water vapor it can hold. The cooler the air, the less water vapor it can hold. So saturation humidity, the Higher the temperature, the higher the saturation humidity. The lower the temperature, the lower the saturation humidity. All right, you kind of think of a summer day, it could be much more humid when it's hotter and when it's cooler. Cooler days, they aren't as humid because on warmer days, the air can literally hold more water vapor because it has a higher saturation humidity. Then we have relative humidity. Relative humidity is the ratio of the absolute humidity to the saturation humidity. So for example, if we had a humidity, say the saturation humidity is 100 air molecules, that's for a given volume of air. At this temperature, this volume of air can hold 100 air molecules. That's the saturation humidity. Let's say the actual humidity, the absolute humidity is there's 50 air molecules in that volume of air. So what is the relative humidity? It would be 50%. It's the actual humidity, 50, divided by the relative humidity, sorry, the saturation humidity, 100, that gives us 50%. Say if there were 75 air molecules, that would be a relative humidity of 75%. Let's say if there was 100 air molecules, then the relative humidity would be 100%. So the relative humidity tells us how much water vapor is in the air compared to how much water vapor the air can hold, right? So if there's a day where there is a 98%, and that's how humidity is presented. Whenever you see the humidity, what's being reported is the relative humidity. And say, oh, the humidity is 98%. What they're saying is the relative humidity is 98%. On days it's raining, the relative humidity is very high. Because what happens is if there's too much. Okay, well, let's take a step back. Remember, saturation humidity is a function of temperature. So you can have air at a given temperature and it has a relative humidity of, say, 75%. But what happens as the temperature of the air decreases? Well, the amount of water vapor the air can hold is also going to decrease. Its saturation humidity decreases. As the saturation humidity of the air decreases with the temperature, how does the relative humidity change? Well, it's going to increase. Why? Because the actual amount of water vapor in the air, the absolute humidity, doesn't change. And so the ratio of the amount of humidity in the air to the saturation humidity is going to increase because the saturation humidity is decreasing. So as the temperature continues to drop, the saturation humidity is going to be less and less and less, and therefore the relative humidity is going to be more and more and more until eventually the saturation humidity is equal to the actual humidity, and the relative humidity will be 100%. What happens if the temperature continues to fall from that point? Well, then the saturation humidity of the air is actually less than the amount of water vapor in the air. So that means there's more water vapor in the air than the air can hold, so that excess water vapor, it comes out of the air. It forms little water droplets, which are clouds, fog, and as enough of those water droplets accumulate, they become heavy enough that they fall down to the ground as precipitation. Right, so that's how rain comes, right? We have falling temperatures of air aloft, and the saturation humidity sinks, it decreases, which causes an increase in relative humidity until eventually the relative humidity is 100% and it begins to rain. Well, so on really foggy days, what's happening is we're at 100% relative humidity, and actually the water vapor is beginning to condense out and form little water particles that scatter light, and that's what makes fog. It lowers the visibility because it's scattering light. So the temperature of the air mass is lowered without changing the absolute humidity. It'll reach 100% relative humidity because at each lower temperature, a lower saturation humidity applies. And so when The relative humidity reaches 100%. Excess water vapor condenses to liquid water. The temperature at which this happens, the temperature for the given conditions at which the relative humidity will be 100% is called dew point. So here we're looking at a weather page. The current weather where I am is 56 degrees Fahrenheit. The humidity, this is the relative humidity, is 90%. And so here's the dew point, 55 degrees Fahrenheit. So if the temperature decreases by 1 degree centigrade, Fahrenheit, then the relative humidity will reach 100%. And if the temperature falls even more, say if it goes down to 54 degrees, then water will begin to condense out and will form dew or fog. And if this is happening aloft, it would form clouds, right? If this is happening high in the atmosphere, it would form clouds. And if enough water was coming out, it eventually would cause rain. So that's what this dew point means. And if the closer the relative humidity is to 100%, the closer the actual temperature is to the dew point. So water, it absorbs, stores, and releases huge amounts of energy when it changes phase between liquid, solid, and gas. Not only does it have to absorb energy to increase in temperature, and it also gives off energy to decrease in temperature, it absorbs and releases energy in the changing of phase from solid, liquid, and gas. In order for ice to melt, ice has to absorb 80 calories of heat per gram in order to melt. This is called the latent heat of a fusion of water. Liquid water, it has to absorb 600 calories per gram in order to vaporize, to evaporate. That's called the latent heat of vaporization. So for 1 gram of water, it takes more heat to melt it than it does to vaporize it. And conversely, if water is going from vapor to a liquid, which is called condensing, it releases 600 calories per gram. And if it has to, that 600 calories of heat per gram have to be removed in order to condense it, or it has to be released. And same thing for water. If water is at 0 degrees centigrade, if you want to freeze it, or if it's at 32 degrees Fahrenheit or 0 degrees centigrade, it doesn't freeze, right? It will just stay at that temperature. In order to freeze it, you got to continue to remove heat. How much heat? 80 calories per gram to freeze it. So question, why do you sweat whenever you're hot? You sweat in order to cool yourself. How does sweating cool your body? Well, if you excrete water to the surface of your skin, what does that water begin to do? It begins to vaporize. And in order to vaporize, it has to absorb heat. How much heat? 600 calories per gram. So for every gram of water evaporating off of your skin, it is absorbing 600 calories of heat. Where is that heat coming from? Well, some of it's coming from the air, but some of it's coming from your body, right? It's absorbing that heat from your body. And so you excrete water to the surface of your skin to help cool yourself. It doesn't work too well if you're wearing a lot of clothing, right? Because that water is not exposed to the atmosphere. And so it's just kind of like it's held to your body and it's not really allowed to vaporize, because in order to vaporize, it has to, be able to turn to a vapor and diffuse. So that's why if you have a lot of clothing on, not only is it the sweating doesn't help cool you, but the clothing is helping hold heat in, right, making you more hot. All right, and that's why also if you put a cold beverage out on a warm summer day, it gets wet, right? They say that the bottle or the can begins to sweat. What's happening is that cold beverage is sucking heat out of the surrounding air, and in the surrounding air is water vapor, and enough heat is being sucked out of it that water vapor is condensing, and so there is a lot of heat stored in that water vapor. And so if you want to prevent your cold drink from warming up quickly, you got to prevent water vapor from condensing on it. And that's why you put them in those little like those little koozie things, right? Because that creates a barrier between the air and your cool drink, and so the water vapor can't condense on it, and all that latent heat of vaporization isn't released into your drink. So in order to from ice to go to vapor, it has to, which doesn't happen too often, at least on Earth, has to absorb the 80 calories to melt, then the 600 calories to vaporize. That's the latent heat of sublimation that happens sometimes on really warm days in the spring, where snow goes right into vapor. Ice to liquid, that's melting, right? 80 calories per gram. Liquid to a vapor, that's just vaporizing. That's 600 calories per gram. And then vapor to ice, that's deposition. That doesn't happen very often on Earth. It has to release 680 calories per gram. So as the sun's energy is absorbed by the surface of the Earth, some of that heat goes into evaporating water. Right? 80 calories a gram are required to vaporize water. Then the water vapor then rises and is carried by the atmosphere over land, where it cools and water vapor condenses out and falls as precipitation. Then it flows as runoff on the surface and groundwater beneath the surface back to the ocean. And you have this cycling of water. This is the hydrologic cycle. So if it wasn't for energy from the sun vaporizing the water from the ocean, there would be no hydrologic cycle. And the continents would be bone dry, right? There would be no water coming to the continents from the atmosphere. All the water coming to the continents is brought to it from the atmosphere, and ultimately it's from water that's vaporized from the ocean. Or maybe and locally it could be a nearby lake, it's a large lake or so forth, or other bodies of water. All right, so now we're going to talk about a process called adiabatic warming and cooling. So air is easily compressed, and as you go lower in the atmosphere, there's more air above pushing down on it, and so there's larger pressure, and that causes the air to get denser and denser close to Earth's surface. As you go further away from Earth's surface, higher in the atmosphere, there's less pressure and the air expands. It's less and less dense. And air is always flowing from regions of low pressure to high pressure. Upward in the atmosphere, it can overcome gravity if the difference in pressure is significant enough. So if you add, and we'll talk about that later, if you add heat to air in the lower parts of the atmosphere, it can expand enough that its density is low enough for it to rise and overcome gravity. As that heated air rises, though, it's under less and less pressure at those higher elevations, higher altitudes, so it expands. This expansion of the air causes what's called adiabatic cooling. Adiabatic cooling is whenever a gas cools, not because heat is being removed from it, and not because energy is being removed from it, but because the gas is allowed to expand, and the amount of energy per unit volume is now lower. Because temperature is the average amount of energy that the molecules of the material have per unit volume. And so if those molecules are just more spread out, the amount of energy the molecules have per unit volume is going to be lower, just because there's going to be fewer molecules per unit air volume. That's why space is really, 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 really cold, because it's almost a vacuum, right? There's very, very, very few molecules, and so there's very little energy, so it's very cold. So that's adiabatic cooling. Energy wasn't removed, it's just that it expands, so it cools. I know I have an air compressor that it's like a 20-gallon air compressor, and it can compress air up to 200 pounds per square inch. And there's a valve at the bottom of it. And if I open up that valve, if it's fully compressed, open up the valve, the air comes coming out the valve. But what's the cool thing is ice begins to develop if it's on like a hard surface, asphalt or plywood beneath it. ice begins to develop on the surface below that valve. Because that air is compressed, whenever it comes out of that valve, it rapidly expands and rapidly cools, and it sucks heat. When it cools, it's sucking heat from the surrounding air into it, cooling the surrounding air, causing the water vapor to condense out and then even freeze. So it's a really cool phenomenon. So you can see that water vapor is condensing and freezing because of adiabatic cooling. Where the opposite happens, if air aloft at higher altitude descends, it is compressed. And as it's compressed, it undergoes adiabatic warming, which means the temperature of the air is increased, not because heat was added to the air, but because now the air molecules are more closely compacted, so there's more energy per unit volume. So it's warmed without adding energy to it. Sometimes you can feel this if you're pumping up a bike tire and you're pumping it very fast, you feel it tire, you can feel it gets a little bit warm, right? Because you're putting compressed air in there. You're compressing the air and it causes it to adiabatically warm. So this volume of air, you can see how large it is up here. It's at 10 degrees centigrade. As it descends, it's under higher pressure and it condenses. It's compressed, sorry. And as it's compressed, it adiabatically warms. Here it's 20 degrees centigrade. Now down here it's 30 degrees centigrade. So the air warmed by descending, not because heat was added to it, but because it was compressed. And that's called adiabatic warming. And the reverse of the process, this 30 degrees centigrade air near the surface, as it rises, it expands. And so it adiabatically cools. It goes from 30 to 20. As it rises even more, it goes from 20 to 10 degrees centigrade. And so air undergoes about a 10 degrees centigrade adiabatic cooling per kilometer rise. So what does that mean? For every kilometer you go up in the atmosphere, the temperature decreases by about 10 degrees centigrade. So if you have a volume of air at 30 degrees centigrade near the surface, if that air moves up 1 kilometer, it'll decrease in temperature by approximately 10 degrees centigrade. It's if there's no water vapor in the air. So that's called the dry adiabatic lapse rate. As the air cools, we know it can hold less water vapor. And so as the air cools, the saturation humidity decreases, so the relative humidity increases. So if you have air that has water vapor in it, and if it's rising in the atmosphere, it's adiabatically cooling. So its saturation humidity is decreasing, so its relative humidity is increasing. And so there's an altitude at which, as humid air rising, at which the temperature will cause the relative humidity equal 100%. That's called a lifting condensation level. And if the air rises above that point at all, the temperature will continue to fall, and the relative humidity will now be, the saturation humidity will be below the actual humidity, and water vapor will begin to condense out. That's how clouds form, right? Clouds form from humid air with water vapor rising up into the atmosphere, and it reaches, and as it rises up, it adiabatically cools because it's expanding. And eventually, it hits a level where the water vapor begins to condense out because the relative humidity is 100% in clouds form. So if you ever notice, clouds always form at the same level. You don't often see, at least from the ground, multiple levels of clouds. Now there are multiple levels of clouds, right? Because there's different amounts of water vapor in the air. But you'll see there's usually kind of like a bottom to that. And the clouds some days look a little lower and some days a little higher if there are clouds. Right, and that all depends on the temperature of the air and the amount of water vapor in the air. So now we have, there's a difference in the rate of heating of land and water because of different in specific heat. You know how the sand heats up much more quickly than the water because of its lower specific heat? Well, that's the same thing with land. Land is roughly rock, and so it has a specific heat. It's roughly 1/5 that of water. So land heats up faster than water. So as the sun's energy, solar radiation is being absorbed by land and water, what heats up fast? Well, rock, because it has a lower heat capacity. So land heats up quickly and it cools down quickly. So in a winter, whenever the surface of the earth is receiving less solar radiation, land cools off much more quickly than the water. So what happens is the air, cool air, begins to sink down over the land. All right, and this creates a high pressure region. Anytime air is moving down, that creates high pressure. Whereas the ocean, it cools down more slowly because water has a higher heat capacity or specific heat. And so the warm, moist air over the ocean is warm and relatively low density, so it begins to rise. And that creates a region of low pressure. And so high pressure develops over the land where the cool, dry air is descending, and low pressure develops over the ocean where the warm, humid air is rising. Now, air along the surface will always flow from high to low pressure. So the cool, dry air will flow from land out over to the ocean. And so what happens is, here's the cool, dry air descending, right? Because cooler air is denser, so it descends, it sinks because denser materials sink. So anytime you have falling air, it's high pressure. Here, the warmer, humid air is rising. So it creates a circulation where along the surface, air flows from high to low pressure. Now, once this cool, dry air gets over here, what happens is it begins to warm up, right? Because the warmer water is radiating heat, warming the air, and also the air is becoming humid from water vapor going into the air. So eventually, what was cool, dry air that flowed out from land over the ocean becomes warm, humid air. It rises and it adiabatically cools, and the water vapor condenses out and begins to fall as precipitation. So we have rain over the ocean in the winter. The opposite pattern happens during the summer. In the summer, whenever the surface begins to absorb more radiation from the sun, the land heats up more quickly. And so the air over the land becomes warmer than the air over the cooler water. And so hot air rises, right? So the warmer air rises. And so that creates, anytime we have rising air, it's low pressure. So it creates low pressure over land. Where the ocean warms more slowly, so the air over the ocean is cooler. It's moist, but it's cooler. And so air is sinking over the ocean, so we have high pressure over the ocean. So the cool, moist air over the ocean is drawn into land and the warm air moves over the land where it's warmed and begins to rise. As it rises, it adiabatically cools, condenses to form rain, and that rain falls out over the land, and that forms the summer monsoons. So with the same process, in the summer though, the land heats up much more rapidly. Okay, so you have cool, moist air flows from high to low pressure. The warmer land heats up the air becomes warm and less dense, so it rises. As it rises, it adiabatically cools, which causes the relative humidity to hit 100%, and water vapor begins to condense out and fall as rain. So we have a lot of rain over land during the summer. And then as the air it returns, right? It comes over here, it cools, it sinks, it becomes humid again, and it comes over here, warms up, rises, the humidity condenses out and precipitates out. This is very pronounced in areas in the tropics, and this is called the monsoon. And in the tropics, they have almost a bi-seasonality, not 4 seasons. They have the dry season in the winter and the wet season in the summer. I know from personal experience, I got married in July. Wife and I went to Costa Rica for our honeymoon. And the prices weren't as high in July as in January. And I read it's the rainy season. And well, it can't be that rainy. Well, Costa Rica is completely surrounded by water. It's a isthmus, right? It's just a strip of land. And so here's the ocean, the Pacific Ocean. Here's Costa Rica sticking up out of the ocean. Here's the Gulf of Mexico. The air over Costa Rica is warmed faster because the land heats up faster. So this air is rising. The cool air from the ocean, cool moist air, is being pulled in to this low pressure. As that cool moist air rises, it adiabatically cools, the water vapor condenses out, forms clouds, then all that water vapor condenses and falls out as rain. And it rained. It's the rainy season and it rained. There was a ton of rain. I've never seen so much rain in my life. In the winter in July, the opposite pattern happens. And so it's very dry. The weather is great. That's why the prices are higher in January than July, right? You get what you paid for. So I learned that lesson the hard way. I should have known better. So here we're going to look at the layering of the atmosphere. So the atmosphere is layered mostly upon density. The lowest layer is the troposphere. It is 8 kilometers thick at the poles and 18 kilometers thick at the equator. And it's thicker at the equator due to the rotation of the Earth. It's warmer at the base and colder above, and warmer air is less dense than colder air. So as a result, the warmer air at the bottom is less dense than the cooler air above, which that leads to instability because less dense warm air wants to rise and denser cold air wants to sink. And so there's a constant mixing of the air vertically in the troposphere, and that mixing is the primary cause of weather. So I ask, well, why is that so? It's because the air in the troposphere near the surface of the Earth is constantly being warmed by the Earth giving off heat, and that's why it's warmer. The tropopause is the boundary of the troposphere and the stratosphere, and above the troposphere is what's known as the stratosphere, which is a stable configuration with cooler, denser air below and warmer, less dense air above. So this instability, this cooler, denser air above and warmer, less dense air below, instability is the primary cause of weather. And so air flows along pressure gradients. From gradients means changes. So it flows and whenever there's a change or difference in pressure, it always flows from areas of high pressure to areas of low pressure. Not only does wind flow from high to low pressure, but the observed direction of the wind is deflected to the right in the northern hemisphere, into the south in the hemisphere, into the left in the southern hemisphere, due to a phenomenon called the Coriolis effect. So the Coriolis effect is a reference frame effect, and it's a result of Earth's rotation. So we are observing the air in the atmosphere moving, but that air is not tied to the Earth. But the Earth is rotating, so we're viewing the air in the atmosphere from a rotating reference frame. So in the speed at which the surface of the Earth is traveling varies as a function of latitude. So for example, at the equator, a point on the equator has to make one full revolution, which is a distance equal to the circumference of the Earth, in one day. Where a point at higher latitude, it has to travel a circle of smaller circumference in the same period of time. So this point of the surface travels at a lower velocity than the equator. And at the very north and south pole, it's actually moving very slowly, just rotating. And so the velocity of rotation is 465 meters per second at the equator and 0 meters per second at the poles. And so bodies, they move to different latitudes. As they do so, they follow curved paths. Well, they appear to follow curved paths. So in the northern hemisphere, air appears to deflect to the right, and in the southern hemisphere, air appears to deflect to the left. And so the magnitude of this Coriolis effect, it increases with increasing speed of the moving body and with increasing latitude. So this Coriolis effect is 0 at the equator, and it becomes more and more pronounced the higher latitude you go. And here we have a video that discusses the Coriolis effect.
It is clear that the Earth is rotating. However, as an observer on the surface of the Earth, the only indication our planet is rotating is in the observation of the sun during the day and stars during the night. Every day the sun rises in the east and sets in the west, but we are completely unaware that we are traveling to the east at hundreds of miles per hour. So just how fast are we moving? Well, at the equator, the rotational velocity of the Earth is an incredibly fast 1,018 miles an hour. If you were to travel from the equator to about 30 degrees north latitude, the rotational velocity would have slowed considerably to about 882 miles an hour. Well, why? As you walk north or south from the equator, you're actually getting closer and closer to the Earth's axis of rotation. Because the surface of the Earth is solid, the rotational velocity will decrease as you walk north or south from the equator, because you're actually getting closer and closer to the Earth's axis of rotation. To understand this better, let's imagine that we take the Earth, a sphere, and flatten it out into a rotating disk, like a merry-go-round. If you were to stand on the edge of the merry-go-round, the rotational velocity would be large, and you would feel like you're going to fly off. However, if you stand in the middle, the rotational velocity would be much less. You would feel like you're barely spinning at all. Now, what if we were to have two people sit on opposite sides of the merry-go-round and try to throw a ball to one another? You can see that as the ball leaves the hands of the person throwing it, it becomes independent of the rotation of the merry-go-round, and therefore follows a straight path. But because the person trying to catch the ball is still rotating with the merry-go-round, they're quickly moved out of the ball's intended path. Because the merry-go-round is spinning counterclockwise, this deflection is to the right. If it were spinning clockwise, the deflection would be to the left. Now, to an observer above the merry-go-round, the path of the ball appears straight. However, to people on the merry-go-round, the path of the ball curves to the right of the intended motion. This experiment demonstrates how the rotation of the merry-go-round appears to cause a deflection in the path of the ball. This also demonstrates how air movement on the Earth's surface can be deflected by the Earth's rotation, a phenomenon called the Coriolis effect. How do we relate the effects of the Coriolis force to air motion in our atmosphere? To answer this question, let's first investigate what would happen to a parcel of air that was initially at rest with respect to the Earth. At 30 degrees north latitude, the parcel is traveling to the east with the Earth. But if we were to shove this parcel at 10 miles an hour to the north, what would happen to its motion? We have already seen from the merry-go-round experiment that the ball would be deflected to the right. But why? The answer lies in understanding something called the conservation.
And if this is a physics course, we'd go ahead and talk about the conservation of angular momentum. But we'll leave that for the physics course. So because of the Coriolis effect, air moving along the surface, it rotates. As it moves, it appears to deflect. And if that air is moving fast enough, then that deflection could be substantial and actually cause the air to spiral inward and create what's known as a cyclone. So rising air, in the northern hemisphere, rising air creates low pressure. And as air moves in towards that low pressure, it begins its counterclockwise rotation. Where sinking air and high pressure, as it moves away, it'll rotate counterclockwise. But this counterclockwise rotation in the northern hemisphere and clockwise rotation in the southern hemisphere is what we see in cyclones. So the atmosphere is what helps facilitate the heat transfer from low latitudes to high latitudes. So as the Earth absorbs the largest amount of heat per unit area along the equator and the tropics, the surface becomes very warm. As the surface becomes very warm, it heats the air above the surface. And so this air becomes warm, less dense, and it rises. And then at high altitude, it moves both towards the North Pole and towards the South Pole, where it cools. As it cools, it begins to sink, condense. And as it comes towards the surface, some of it moves down back towards the equator on both the northern and south hemisphere. but some of it moves towards the pole. And as it moves towards the pole, it warms again, and then it rises, and it cools, and it sinks, and some of it moves this way, some of it moves that way, and it creates what are called these convection cells. So these convection cells are air rising and then falling in Earth's atmosphere. And in each hemisphere, there are 3 convection cells. The 2 that are on both sides of the, well, I have to say, before I say the equator, there is this red line called the ITCZ. The ITCZ stands for the Intertropical Convergence Zone. So it's called a convergence zone is because you can see these winds. These are called the trade winds. They're the surface winds at these low latitudes. They blow and they converge with each other along this ITCZ. So that's why it's called CZ, convergence zone. IT stands for intertropical. So this convergence zone, it always exists within the tropics. Sometimes it's north of the equator, sometimes it's south of the equator, sometimes it's right at the equator. Depends on the time of year. And so going back to the convection cells in Earth's atmosphere, there's 3 to the north of the ITCZ and 3 to the south of the ITCZ. And they mirror each other. So right next to the ITCZ, we have the Hadley cells, where the trade winds, they blow, they converge, and they rise, and they sink, and they make this convection cell, a Hadley cell. Some of the air in the Hadley cell, as it sinks, it moves this way towards the pole, where it warms, it rises, then it sinks and creates another convection cell. And then we have a 3rd convection cell, which is the polar cell. And here is what's called the polar front. This is where the warm air of the ferrule cell meets the cold air of the polar cell. And it forms like it's known as a polar front. So these Hadley cells, they create bands of high pressure at 30 degrees north and 30 degrees south. Why? Because that's where the air is descending. Remember, anytime we have air descending, that creates high pressure. So high pressure zones at 30 degrees north and 30 degrees south. Because, you know, high pressure usually always means good weather because air is sinking. It's only whenever air rises, in particular, moist air rises, that you have bad weather. And that's low pressure when air is rising. Air flows away from the high pressure zones, and then air flows over land from the poles to collide at the polar front around 60 degrees north, 60 degrees south, or here's the polar front. So the descending air, this high pressure zone, the edge of the Hadley cell, some of it flows northward and it converges with the cooler air at about 60 degrees north and south, and it's called the polar front. So we have the Hadley, ferrule, and polar cells, and then we have the convergence of air at the ITCZ. And we have rain at the ITCZ from the air rising, and then we have the polar front. So those are the highlights of this atmospheric circulation. So this global wind pattern of these convection cells, it can be modified by continental masses, mountain ranges, seasons, or even the Coriolis effect. So we look at North America now as an example. Now in the atmosphere, we call a volume of air that has the same temperature and humidity, we call it an air mass. So any volume of air that has the same physical conditions, temperature and humidity, we call that an air mass. And with North America, what happens is there's cold polar air masses to the north and warm tropical air masses to the south. The dry air masses, they move over land. Wet air masses, they move in from over land. That's why they're dry, because they're coming from land. Anything that's coming from over water is moist. So this is dry because it's coming from land. This is dry, it's coming from land. All these air masses are moist because they're coming in from water. So the dominant air mass movement is from west to east. Why is that? Because the prevailing winds at our latitudes are what are known as the westerly winds. So as this air moves towards the North Pole along the surface, it's deflected to the right in the northern hemisphere. So this air is moving to to the northeast. And so those westerly winds, they move weather or air masses from the west to the east in the northern hemisphere. That's why if you're ever watching the weather, the meteorologist is always referencing what's happening over here, right? They never talk about what's happening over the Atlantic, because it's what's over here that's going to be coming our way. And so the Pacific air masses, they have more impact on the weather of North America than the Atlantic air masses. Sorry, than the Atlantic Ocean. So what's going on in the Pacific Ocean has much more influence on our weather than what's going on in the Atlantic Ocean. That's besides hurricanes. And so a front is a boundary between two air masses. So air masses, so two different air masses that have different temperatures and humidities have different densities. And whenever two air masses of different density come into contact with each other, they don't want to mix. So fluids of different density don't want to mix. And so they form a boundary between them. And that boundary is known as a front. And so a front is a sloping surface that's separating air masses with different temperature and moisture content. And it's along these fronts that severe weather can be triggered. And so we have violent storms. So here is a warm, humid air mass to the south moving this way, a cold, dry air mass to the north moving this way. And this is a front. If a low pressure anomaly develops along this front and air begins to move in toward it, then this front separates into a cold front and a warm front. So a cold front is a moving boundary in which cold air is advancing behind it, where a warm front is a moving boundary in which warm air is advancing behind it. So this is a cold front because cold air is coming in behind it. And this is a warm front because warm air is coming in behind it. Now, if we take a cross section, because this is a bird's eye view from A to B, we see that at the warm front, this warm air is moving into this cold air. Well, cold air is denser, so it wants to stay at the surface. So the warm air just gradually flows up over top of the cold air. And so it gradually gains elevation, and so it gradually cools, adiabatically cools, and then the water vapor gradually precipitates out, and you have widespread precipitation. Nothing's concentrated. Whereas the cold front, you have this cold, dense air that's hugging the surface because it's denser, moving in, and this warm air is being pushed up out of the way as this cold air moves in. So this warm, moist air is being pushed up very dramatically, and so you have warm, moist air moving up into the atmosphere in a concentrated region. So all that water vapor that has that latent heat of vaporization, which is energy, is being pushed up into the energy at a localized area. And so that energy is released, it warms the upper atmosphere, which makes the air aloft even less dense and rises with more vigor, which lowers the pressure, which pulls in more air. So it creates this positive feedback loop, creating a large storm. So cold fronts or cold air masses, they move in under warm air masses, lifting it up, and it forms tall clouds and thunderstorms. We'll talk more about that when we discuss severe weather. So another feature of the general circulation of the atmosphere is the jet stream. So the jet stream is a relatively narrow band of high velocity, around 200 kilometers per hour. The high velocity wind flowing from west to east at high altitude. So what happens is the pressure decreases more slowly moving upward in altitude through warm air than it does in cold air. So at high altitude, the warm air to the south, the pressure here is going to be higher because the pressure decreases more slowly than the pressure up there. So the air wants to move from the warm to the cold, so it wants to move that way. But the Coriolis effect deflects the air to the right. So it begins to move this way, forming the jet stream. The jet stream in the southern hemisphere flows in the opposite direction. So warm air aloft has higher pressure than cold air. Warm air flows towards the cold air, towards the poles. The spin of the Earth turns poleward air, and causes it to flow high speed in the jet stream from the west. So the turning of the air flowing towards the poles to flow from west to east in the northern hemisphere is due to the Coriolis effect. And there's another subtropical jet around 30 degrees north, and then there's a polar jet. So, but the jet stream usually acts as the boundary between the polar cell and the warmer feral cell. And so there's significant variation in air pressure and wind patterns by hemisphere and season. So seasonal changes are not so great in the southern hemisphere because most of the surface is water, and because most of the surface is the same material, there's not as much differences in surface temperature as the seasons change. Where the northern hemisphere, there's much more of a mix of water and land, and because of that, there's more of a temperature imbalance between the surface as the surface begins to receive more energy during the summer or less energy during the winter. So that temperature imbalance on the surface between land and water creates basically pressure differences in the atmosphere, and pressure differences causes the movement of air and creates winds. So winter has strong high pressure air masses of cold air over continents, and summer has thermal lows over continents. And then there's the Pacific and Bermuda high pressure system. So in the winter, the air cools down quicker. So the air begins to sink over land. So you have high pressure over land in the winter, and low pressure air over water in winter. In the summer, the land heats up quickly, and air begins to rise over land. So you have low pressure over land and high pressure over water. And so the surface and near surface ocean waters, they absorb and store huge amounts of solar energy. Some of the solar heat is transferred deeper into the ocean by tides and winds. The surface and deep ocean circulation, it transfers heat throughout the ocean and affects global climate. And so the movement of the ocean also helps transport heat from low to high latitudes, just like the atmosphere does. And this heat transport by the ocean has climatic impacts as well. The surface circulation in the ocean is mostly driven by the winds. So the wind blows across the water and pulls the water along with it, creating surface circuits. So the movement of the top layer of water drags on the layer beneath it, and etc. And so this results in water moving with the wind down to about a depth of 100 meters. So we have the surface circuits or surface circulation of water in the ocean that's driven by the wind that extends to about 100 meters depth. Then these wind-driven flows, their directed or flow directions are modified by the Coriolis effect, and so that changes their direction. And also, whenever they run into continents, they're forced to turn directions, these currents. So the Coriolis effect and deflection off of continents is what turns these surface currents. These surface currents, they help carry heat from low to high latitudes. So here you can see a map of some of these surface currents. So the red arrows are warm water currents, the blue are cool. So you can see warm water moving to the north, taking heat to the north, and then you have cool water returning back down. So warm water being carried to the north, warm water being carried to the south, cool water returning, cool water returning. And so you'll see that the rotation of the surface circuits is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. In these circuits they're called gyres, ocean gyres. Then we also have deep ocean circulation. So the ocean is layered based upon density, so it gets progressively denser with depth. And so water density increases with lower temperature and increased salinity. But there is this slow overturning or vertical circulation of the ocean. It's very slow. That's caused by small changes in density. It's known as the thermohaline current because it's driven by difference in temperature. That's the thermo part of the name, and difference in salinity. That's the haline part. And so this is the overturning circulation. So this is cold water from the bottom rising to the surface, and warm water from the surface is sinking to the bottom. So the ocean water has higher density at high latitudes where it's cooler. In the Arctic and Antarctic, where fresh water is frozen into sea ice, where the remaining water is made saltier. And in warm climates, where fresh water is evaporated and the remaining water is saltier. That's where we have a higher density water. And the densest ocean water, it forms in the northern Atlantic and the Southern Ocean. And so that's the densest water that forms because it's so cold and so salty, and so it eventually sinks in the northern parts of the ocean to the bottom. And then it's near the equator that the cooler water rises to the surface. And so this slow overturning of the ocean actually helps take heat from the surface down into the depths of the ocean. And the one problem is if the whole ocean warms too much, that circulation shuts down. We see this happening on a small, on a kind of like a small scale sometimes in bodies of water where they stop circulating. If they stop circulating, then there's no oxygenated water taking to larger depths, and that has a significant impact for sea life and other ecological factors. And so it's also a way of sequestering or burying heat. And so for a while, scientists weren't sure why the Earth's climate wasn't warming at the rate they expected based upon the CO2 emissions. But then they finally realized that a lot of that heat was being taken down to the larger depths of the ocean by this thermohaline circulation. And this thermohaline circulation, it takes about 100 to 150 years for it to make one complete cycle. And so after 100 some years, the water that was coming back up was now a little bit warmer than it used to be. And as a result, the water at the surface, coming up at the surface, wasn't as cold, so it couldn't absorb as much heat. And so then we began to see the warming begin to accelerate to the pace that we were expecting it. Scientists were expecting it. So this thermohaline circulation almost acts as a buffer, preventing the atmosphere from warming as fast as it just would on its own. But the problem is there's only so much heat the ocean can absorb before it stops overturning and it no longer sequesters any of that heat. And so whenever that happens, there'll be much larger problems. So that concludes our lecture on external energy and how it fuels weather and climate. Thank you very much.